Welcome to Orbit Observer. It's lovely to have you here wherever you are tonight. Maybe you're under a blanket with the lamp still on. Maybe you're on a couch with the world gone quiet, or on a train, or just lying in the dark with your eyes already half closed. However you've arrived, and that's enough. Settle in, there's nowhere to be. Tonight, we're going to drift slowly and softly all the way out to Mars. Not to the red planet itself, not really. We're going past it to the two small things that circle it, two little moons, two lumpy, dark, doomed little worlds that almost nobody ever stops to think about. And we're going to spend this whole quiet stretch of night with them, one fact at a time, no rush at all. And if you enjoy these slow journeys and want more of them, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you already subscribed, drifting off with me again tonight, thank you. Truly. Before we go any further, I'd love to know one small thing, and you can answer it in the morning if you'd rather just close your eyes now. Where in the world are you listening from tonight? What time is it in your corner of the night? Leave it in a comment whenever you like. It's a lovely thing, knowing there's a whole quiet map of people drifting off together. Now, let me start with something strange, something true. Imagine you're standing on the surface of Mars. The sky is a dusty pinkish color in the day, and at night it goes to a deep, soft black. And up there, in that black sky, there's a moon. A small one. But here's the strange part. This little moon doesn't rise where you'd expect it to. It comes up in the west. The wrong side. It climbs up out of the western horizon, crosses the sky, and sets in the east. Backward. The opposite of everything our own sky does, the opposite of the sun, the opposite of the stars. And it doesn't do this once a night, the way our moon takes its slow, patient march from one side of the sky to the other across long hours. No, this little Martian moon is in such a hurry that it crosses the whole sky and sets, and then rises again and crosses again, twice, before a single Martian night is even over. Twice. You could lie on your back on the cold red ground and watch this moon make its whole backward journey across the heavens, and then watch it do the entire thing all over again, all before one sunrise ever comes around. That little hurrying moon is called Phobos. And tonight I want to tell you about Phobos and about its smaller, quieter sister moon, Deimos. Because there's a secret hiding in these two. One of them is falling, and the other one is running away. We'll get to all of that slowly in its own time. No need to hold on to any of it. The ideas will still be here whether you stay awake for them or not. If you drift off somewhere in the middle, that's perfectly fine. That's rather the point. I'll keep talking softly and the moons will keep doing what they've been doing for billions of years. So let's begin, shall we? Let's start with the simplest thing of all, just the two of them side by side, so you can picture them. Mars has exactly two moons. Only two, that's the whole family. No more have ever been found, no matter how carefully anyone has looked. Just Phobos and Deimos, the two of them going around and around the red planet in the dark. And both of them are tiny. I mean, genuinely tiny. If you've ever looked up at our own moon, big and round and bright enough to throw shadows, then I want you to set that picture aside entirely, because the moons of Mars are nothing like that. Nothing like it at all. Phobos is the bigger of the two, and even Phobos is small. It measures roughly 27 kilometers across in its longest direction, by about 22, by about 18. And I'm giving you three numbers there for a reason, because Phobos isn't a ball. It isn't round, it's a lumpy thing, longer one way than the other, shaped more like a potato than a planet. 27 kilometers by 22 by 18. If you've ever driven across a small city, you've covered more ground than that. The whole moon, end to end, is shorter than a morning commute. And Deimos, the little one, is smaller still, about 15 kilometers across one way by 12 by 11, even lumpier, even more like a chip of broken stone than a proper moon. Deimos is so small that in principle, if you could somehow stand on it and walk in a straight line, you could cross the entire moon in an afternoon. The whole world, side to side, a single afternoon stroll. Try to hold that picture for a moment in the dark. Moon so small you could walk across it before dinner. Now you might be wondering why they aren't round. Why aren't they nice, neat spheres like our moon, like the planets? And it's a lovely, simple reason. A world only becomes a ball if it's big enough. If there's enough of it, then its own gravity, its own weight, pulling inward from every direction at once, slowly crushes it into a sphere. Mountains can't stand too tall. Everything gets pulled down and rounded off, but Phobos and Deimos are far too small for that. There just isn't enough of them. Their gravity is so feeble it can't smooth them out, so they keep the shapes they were given, the jagged, irregular, broken shapes of rock. They look like what they are, two pieces of rubble drifting around a planet. They're among the very smallest moons in the whole solar system that anyone has ever studied up close, little chips of darkness. And dark really is the word. Their surfaces hardly reflect any light at all. Phobos and Deimos throw back only about 6 or 7% of the sunlight that lands on them. The rest just vanishes into the rock. To give you something to picture there, fresh asphalt, the black tar of a newly laid road, reflects more light than these two moons do. They are darker than a wet road at night. Two soot-dark stones almost swallowing the sunlight that falls on them, circling the red planet in near invisibility, which makes it all the more remarkable that anyone ever found them at all. So let's go back, way back, to the summer of 1877, and to a man with a telescope and an aching, tired patience. His name was Asaph Hall. He was an American astronomer, and he worked at the United States Naval Observatory in Washington. And in the August of that year, he was hunting. He was searching the space right up close around Mars in the glare of the planet itself, looking for anything that might be circling it. People had wondered for a long time whether Mars had moons. Nobody had ever found one, and Hall had been at it for nights, peering into the eyepiece, his eyes straining against the brightness of the planet, finding nothing. Nothing. Just the hard, bright disk of Mars and the empty dark around it. There's a story here, and it's a true one, and it's one of my favorite small moments in the whole history of looking up. Asaph Hall was tired. He'd been searching and searching, and he was close to giving the whole thing up. And his wife, her name was Angeline Stickney Hall, is the one who, the story goes, urged him to keep going. One more night, don't stop yet, one more night. And so he did. He went back to the telescope. He used the great instrument of the observatory, a refractor with a lens 26 inches across. At the time, that was the largest refracting telescope anywhere in the world. The finest light-gathering eye on the planet pointed at Mars. And with it, on the night of August the 12th, 1877, Asaph Hall saw it. A tiny point of light near Mars that shouldn't have been a star. A moon. He had found the smaller, farther one first, the one we now call Deimos. And then he kept watching, night after night. And 6 nights later, on August the 18th, he found the second one. The bigger, closer, faster one. Phobos. 2 moons of Mars found within a single week by one tired man who almost gave up, talked into one more night by his wife. And he didn't forget her. That great scar on Phobos, the enormous crater that we'll come back to later tonight, the one that nearly destroyed the whole moon. It's named Stickney, after Angeline Stickney Hall. Her maiden name written forever onto the face of the moon her urging helped to find. I rather love that. Every time astronomers say the word Stickney, they're saying her name. Now, why 1877? Why that particular summer? Because of something astronomers call an opposition. Mars and Earth are both going around the Sun, but at different speeds, on different tracks. And every so often the two planets line up on the same side of the Sun and come unusually close to each other. 1877 was one of those close approaches, a particularly good one, and that's what gave Asaph Hall his window. Mars came near, big and bright in the eyepiece, and in that closeness the two faint little moons could finally be teased out of the glare. And here's a quiet little detail, the kind that pleases me in the dark. That very same close approach of Mars, that same 1877 opposition, was when another astronomer, an Italian named Giovanni Schiaparelli, was busy mapping Mars and drew the famous lines on its surface that he called canali, channels, those markings that would later spark all those stories of Martian canals and Martian engineers. So the same near passage of Mars that gave us its two moons also gave us its most famous illusion, the same bright summer, two discoveries and one beautiful mistake all at once. So now Hall had his two moons, and they needed names. The names came from a man called Henry Madden, who was a science master at Eton, a teacher. He suggested them to Hall, and he drew them out of the oldest of stories, out of Homer's Iliad, the ancient Greek poem of the war at Troy. And the names he chose fit the war planet perfectly. Because in Greek mythology, the planet we call Mars was the god Ares, the god of war. And Ares had two companions, two figures who went with him into battle. Their names were Phobos and Deimos. Phobos means fear, and Deimos means dread or terror. And in the old stories, these two, fear and dread, were the sons of Ares himself, the children of the war god who rode out with their father into the slaughter, the embodiments of the panic and the horror that war brings with it. So think about that for a moment as you lie there in the warm dark, two small dark moons going around the red planet of war. And their names are Fear and Dread, the god of battle, circled forever by his own two sons, by terror itself. There's something almost tender about it once you sit with it. Not frightening at all, really. Just two faithful little companions keeping their endless watch around their father, the way they always did in the stories. Fear and dread drifting in the quiet dark. And the names didn't stop there. The little features on these moons, the craters and the marks, were given names too, and the choices are lovely. The features on Phobos are mostly named after astronomers and after people and places from a famous old book. The features on Deimos are named after writers, specifically the writers who, strange as it sounds, wrote about the moons of Mars before anyone had ever actually seen them. And that brings us to one of the most uncanny little curiosities in this whole story. I have to tell you about it, but I want to tell you carefully, honestly, because it gets exaggerated all the time, and the truth is gentler and stranger than the exaggeration. Go back to the year 1726. That's more than 150 years before Asaph Hall ever pointed his telescope at Mars. In 1726, the writer Jonathan Swift published Gulliver's Travels. You may know it as the story of the man who washes up among the tiny people of Lilliput. But there's another part of the book, a later voyage, where Gulliver visits a strange floating island called Laputa, an island of astronomers and philosophers who spend all their time lost in thought and study. And Swift wrote that these astronomers of Laputa had discovered something remarkable. They had found, he wrote, that Mars had two small moons, two of them, going around the red planet. More than a century and a half before anyone on Earth actually saw them, Jonathan Swift sat down and wrote that Mars had exactly 2 little moons. And it gets stranger because Swift didn't just say there were 2. He gave them invented details. He wrote down fictional numbers for how far out they orbited and how quickly they went around, and when you compare his made-up figures to the real moons that Hall would later find, they're not exact, but they're eerily in the right ballpark. 2 moons, close in, going around fast. He more or less got the shape of the truth. Now here's where I want to be honest with you, because this is the part that gets told as if it were magic, and it isn't. Swift almost certainly wasn't seeing the future. He was making an educated guess. People at the time knew that Earth had 1 moon and that Jupiter had 4 that had been discovered. So the thinking went, in a rough and reasonable way, Mars sits between Earth and Jupiter, so perhaps Mars has a number of moons in between, a tidy 2. It was a logical guess dressed up in a story, a lucky, clever pattern, not a prophecy. But oh, what a lucky guess, to sit down 150 years early and write down the right number of moons and roughly the right kind of orbits. There's a quiet wonder in that, even when you know it was only reasoning. The universe, every so often, lets a guess land beautifully, and Swift wasn't even alone in this. A few decades later, in 1752, the French writer and philosopher Voltaire wrote a story of his own called Micromegas, a tale of a giant traveler from the stars who comes to visit our little world. And in that story, Voltaire also mentioned that Mars had 2 moons. He was very likely just echoing Swift, borrowing the same clever idea, but there it is again. 2 writers decades apart, both writing 2 moons around Mars long before anyone had laid eyes on them. And so when the real moons were finally found, and when astronomers came to name the marks upon the smaller one, Deimos, they remembered. There is a region on Deimos named Swift, and another named Voltaire. 2 writers who imagined Mars's moons into being before they were ever seen, their names now carried softly around Mars by the very moons they dreamed up. I find that one of the loveliest small justices in all of astronomy, the dreamers got their names written onto the dream. So there they are now, our 2 little worlds, Phobos and Deimos, fear and dread, 2 dark lumps of rock, smaller than cities, found in a single week of a long-ago summer by a tired man and his patient wife, named for the sons of the war god, written about by poets and dreamers more than a century before anyone saw them. 2 faithful little companions circling the red planet in the black. But I told you at the very start that one of these moons has a secret, that one of them is falling and the other is running away. And we haven't touched that yet, not really. We've just gotten to know them, the way you get to know 2 quiet strangers before you learn what's really happening in their lives. So let me begin to draw the thread. Let me start with the falling one, with Phobos, because everything about Phobos, every strange thing, the way it rises in the west, the way it crosses the sky twice a night, the way it hurries, all of it comes from one simple fact. Phobos is close, astonishingly, impossibly close to Mars, closer than any other known moon in the entire solar system is to the planet it circles. No other moon around any other planet that we know of hugs its world the way Phobos hugs Mars. But that, I think, is exactly where we should slow down, because the closeness of Phobos is the beginning of its whole story. The reason it rushes, the reason it rises backward, and in the end, the reason it's doomed. And it deserves to be taken gently, one piece at a time. So let your shoulders go heavy for a moment. Let the blankets settle. We have all the time in the world, and Phobos isn't going anywhere, not for a few million years yet. Picture Mars hanging there in the dark, a rust-red world smaller than our own Earth. And now picture this little potato of a moon, Phobos, going around it. But not far away, the way our moon sits way out from Earth, 250,000 miles off, small and distant and slow. No. Phobos skims along just above the Martian surface, hugging the planet close, racing around it like a low, fast bird circling a tower. So close that it cannot help but hurry. So close that from the ground it comes up in the wrong place and crosses the sky the wrong way and does the whole thing twice before morning. And the reason it's so close, and what that closeness is slowly, quietly doing to it, well, that's where we'll go next. Into the falling, into the slow, patient, unstoppable descent of a little moon toward the planet it has circled for so long. But not yet. For now, just hold the picture. The red planet. The two dark companions, fear and dread, turning in the silence, one of them skimming low and fast and close, the other drifting far and slow and quiet, out in the deeper dark. And whatever time it is, wherever you are, let it all turn gently in your mind while you rest. We're only just beginning and there's no hurry at all. Welcome to Orbit Observer. It's lovely to have you here in whatever quiet corner of the world you've found tonight. Maybe there's a lamp still on. Maybe it's already dark and this is just a voice in that dark keeping you company while the rest of the day finishes letting go of you. Wherever you are, settle in. You don't have to follow every word. You don't have to remember a single fact by morning. If you drift off somewhere in the middle of all this, that's exactly as it should be. The moons will still be there, turning slowly around Mars, long after you've fallen asleep and long after you've woken again. And before we drift in too deep, if these slow journeys are the kind of thing that helps you rest, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on that quiet support more than you'd think. And if you're already here, already part of this, thank you, truly. So tell me, before your eyes get too heavy, where in the world are you watching from tonight? What time is it in your corner of the dark? I always like to imagine all of you out there, scattered across the night, drifting off to the same soft story. Now, let's go back to those two little moons and let's take it slow. I told you Phobos rises in the wrong place and crosses the sky the wrong way, twice before a single Martian night is through. And I want to just sit with that for a moment, because it's one of the strangest, gentlest facts about this whole little world, and it's worth turning over slowly in your mind like a smooth stone in your palm. Here on Earth, the moon rises in the east, the sun rises in the east. Almost everything in our sky comes up over one horizon and slides down the other, east to west, because the Earth turns beneath them. We're so used to it that we never even think about it. But Phobos breaks that rule. It rises in the west, climbs across the Martian sky, and sets in the east, backward. And the reason is simply that Phobos is in a hurry. It races around Mars faster than Mars itself can turn. Mars spins on its axis in a little over 24 hours, much like Earth does. But Phobos finishes a whole lap around the planet in just about 7 hours and 39 minutes. It laps the planet. It overtakes the very ground below it. And so to anyone standing on the rust-colored sand looking up, the little moon seems to swim against the current of the sky, coming up where everything else goes down. And because it moves so fast, it doesn't just cross the sky once and call it a night. It rises in the west, sails over, sets in the east, and then a few hours later, it does the whole thing again. Twice in one Martian night, a person could watch this little moon make its backward journey across the stars before the sun finally comes around to start a new day. Imagine that. Lying on the cold red ground, watching a small dark moon hurry over you, slip below the horizon, and come back to do it all over again before dawn. There's something almost restless about it. A little moon that can't quite hold still. Now, before we go any further into Phobos and its hurrying, let's get our bearings. Let's get a sense of just how small these two companions really are. Because part of what makes them so easy to love is how modest they are. These are not grand worlds. These are not the big bright moon we know. Mars has exactly two moons, just two. Phobos and Deimos, and as far as anyone has ever found, that's all there is. No others hiding in the dark. And both of them are tiny, almost comically tiny, next to the great pale moon that lights our own nights. Phobos is the larger of the pair. And even Phobos is barely a moon at all by our standards. It measures only about 27 kilometers across at its widest, and less than that the other ways, roughly 27 by 22 by 18, which means it isn't a ball at all. It's lumpy, lopsided, shaped more like a battered old potato that's been knocked around in a drawer than like the round moon you'd draw as a child. You could, if you were patient and didn't mind the cold, drive across the whole of Phobos in well under an hour. And Deimos is smaller still. Deimos is only about 15 kilometers across at its longest, 15 by 12 by 11 give or take. Smaller than many cities. Small enough that you really could cross the entire moon on foot in an afternoon, if walking on something that small were possible at all, which, as we'll see later, it sort of isn't. Neither one is round, and the reason is a quiet little law of nature. To pull yourself into a smooth sphere, a world needs enough gravity to crush its own rock into shape, to round off the corners, to settle into a ball. Big worlds do this easily. Earth did it, the moon did it, but Phobos and Deimos are simply too small. Their own gravity is far too feeble to reshape them, so they keep whatever lumpy, broken, irregular form they were left with. They look like exactly what they may well be, chunks of dark, ancient rock, never melted, never smoothed, just drifting and turning in the silence above Mars. And they are dark. This is one of those small details I find oddly soothing. If you could hold a piece of Phobos in your hand, it would be among the darkest things you've ever seen. These moons reflect only about 6 or 7% of the sunlight that touches them. That's darker than asphalt, darker than coal. So when you picture them up there beside the red planet, don't picture two bright silver coins. Picture two faint charcoal smudges, two soft grey shadows catching only the smallest hint of the distant sun, quiet, dim, and easy to miss, which is exactly why, for most of human history, nobody knew they were there at all. Because here's the thing, we've had Mars in our sky forever. People have watched that red, wandering point of light for thousands of years, named it after the god of war, told stories about it. But nobody saw its two little moons until the late summer of 1877. And the story of how they were finally found is a gentle one, with a quiet hero at the heart of it, who isn't the man whose name usually gets remembered. The astronomer was Asaph Hall, an American, working at the United States Naval Observatory in Washington. And in the August of 1877, the conditions were just right. Every so often, Mars and Earth come unusually close to each other in their orbits, a moment astronomers call an opposition. And that summer was one of those rare close approaches. Mars hung larger and brighter in the sky than it usually does, and Hall meant to use that closeness to search the space right beside the planet for any faint moons that might be hiding in its glare. It wasn't easy. The trouble with looking for something dim right next to something bright is that the bright thing drowns the dim thing out. Mars itself kept washing out the faint smudges he was hunting for. Night after night, Hall searched, and night after night, nothing. And the story goes, or and it's a well-loved story even if it's told a little softly around the edges, that he had very nearly given up, that he was ready to set the whole search aside, and it was his wife, Angeline Stickney Hall, who told him to try one more night, to not give up just yet, stay with it a little longer. So he did. And on the night of August the 12th, 1877, peering through the great 26-inch refractor, the largest refracting telescope in the entire world at that time, Asaph Hall finally caught it. A tiny point of light holding its place beside Mars, the first of the two moons. That one was Deimos, the smaller, more distant one. And then, just 6 nights later, on August the 18th, he found the other, Phobos, the larger, faster one, hugging close to the planet. 2 moons found within a week of each other after the whole long history of the world had passed without anyone knowing they were there. And that same close approach of Mars, that very same opposition that gave Hall his window, it's the one during which another astronomer, an Italian named Giovanni Schiaparelli, was busy mapping the surface of the planet itself, sketching the lines he called canali, the famous so-called canals of Mars that would set imaginations running wild for decades after. So the 2 little moons stepped out of the dark in the same season that Mars itself was being mapped as never before. A busy, glowing summer for the red planet. Now the names, Phobos and Deimos, they weren't named by Hall himself, not really. The suggestion came from a man named Henry Madan, a science master at Eton over in England, who reached back to Homer's Iliad for inspiration. And it was a fitting place to look, because Mars, the war god, has 2 companions in the old Greek myths, Phobos and Deimos, whose names mean, more or less, fear and dread. The sons of Ares, the Greek god of war, who is the very same figure the Romans called Mars. In the old stories, these 2 ride alongside their father into battle, the spirits of fear and terror that go before an army. So when the moons of the war planet needed names, who better than the war god's own sons? Fear and dread, turning quietly around their father, just as the myths imagined them at his side. And the craters and features scattered across these little worlds carry their own gentle theme. On Phobos, many are named for astronomers, and some for people and places out of Jonathan Swift's Gulliver's Travels. On Deimos, the features honor writers who, strangely enough, wrote about the 2 moons of Mars before anyone had ever actually seen them. Which brings me to one of the loveliest little curiosities in this whole story, and one we should be honest about as we tell it. Long before Asaph Hall ever pointed his telescope at Mars, writers had already imagined that the red planet might have 2 small moons. The most famous of them was Jonathan Swift. In 1726, more than 150 years before the moons were actually discovered, Swift wrote, in Gulliver's Travels, that the astronomers of his floating island of Laputa had found 2 small moons circling Mars. 2. The right number. And he even gave them imagined details about how they moved, details that turned out to land surprisingly close to the truth. Now, I want to be gentle and clear about this because it's the kind of thing that gets dressed up as prophecy. It almost certainly wasn't. Swift had no secret knowledge. The best guess is that it was simply a thoughtful, educated bit of imagining. He knew Earth had 1 moon and that Jupiter had several, and Mars sits between them, so 2 felt like a reasonable, tidy guess for a planet in the middle. A coincidence that happened to age remarkably well, not magic, just a lucky, lovely guess. And Swift wasn't alone. A few decades later, in 1752, the French writer Voltaire wrote a short story called Micromegas, and he too gave Mars 2 moons, most likely echoing Swift's idea rather than inventing it fresh. So 2 of the great literary minds of their age had both, in their own way, granted Mars the very pair of companions it really did turn out to have. And that is exactly why, when those features on Deimos needed names, two of the largest were called Swift and Voltaire. A quiet thank you carved into a little moon to the writers who imagined it first. So there they are, two dark, lumpy, ancient little worlds found in a single warm week of 1875 and 77 by a man who almost gave up and a woman who told him not to, named for fear and dread dreamed of by novelists a century early. And already, even now, while you lie there warm and still, one of them is quietly falling toward Mars, and the other, just as quietly, is slipping away. One moon is dropping closer every single year. The other is drifting off into the deeper dark, a little farther each time around. Two opposite fates set in motion long ago, unfolding so slowly that we'll never live to see either one finish. But the falling, the slow, patient, unstoppable descent of little Phobos, and that's the next thread we'll follow. So just rest here a moment longer first. No rush at all. Phobos then. Let's go there slowly. Of all the moons circling all the planets in this solar system, and there are hundreds of them now, hundreds of little worlds and captured rocks and icy bodies turning in their quiet orbits, Phobos holds one distinction that no other moon can claim. It is the closest moon to its planet. Not just the closest moon to Mars, the closest moon to any planet that we have yet found. It skims along just above the Martian surface, threading the gap between Mars and empty space at an altitude of roughly 6,000 kilometers. 6,000. That sounds like a great distance until you realize that our own moon sits nearly 64,000 kilometers above Earth. Phobos is 10 times closer to Mars than our moon is to us. If you were standing on Mars and looked up at exactly the right moment, Phobos would not be some distant point of light. It would be a real thing above you, a lumpy, potato-shaped body crossing the sky, close enough to make out its shape, close enough that on a clear Martian night you could, if your eyes were sharp, just barely catch the shadow of Stickney crater as a dark mark on its face. The orbital radius, the distance from the center of Mars to Phobos itself, is about 9,376 kilometers. That number is worth holding for a moment. The planet Mars has a radius of its own, roughly 3,390 kilometers, which means the gap between the top of the Martian atmosphere and the surface of Phobos passing overhead is not wide at all. It is a narrow thing, a sliver of space, and Phobos fills it, orbiting so close that it falls below the horizon for anyone standing too far north or south on Mars. If you were near the Martian poles, you would never see Phobos. It simply never rises. It orbits too low, and the curve of the planet hides it from view. Only observers within a certain band around the equator ever get to watch it cross the sky. It is a moon that belongs, in a way, only to the tropics of a world that has no tropics in any warm sense. Now, the speed. This is where Phobos becomes something genuinely strange. Mars rotates once every 24 hours and 37 minutes. A Martian day called a sol, almost the same length as an Earth day, close enough that it can feel comforting to imagine the sun rising and setting there on a rhythm not so different from our own. Mars spins slowly, steadily, carrying its rust-colored plains and ancient craters around beneath a thin, pale sky. And for most of the moons in the solar system, this is the simple arrangement. The planet spins, and the moon takes much longer to complete one orbit. So the moon drifts from east to west across the sky, like the sun, like the stars, following the planet's rotation. Phobos does not do this. Phobos orbits Mars in just 7 hours and 39 minutes. 7 hours and 39 minutes to complete a full circle around a planet. It is moving so fast, orbiting so low and so furiously, that it laps Mars's own rotation. Mars turns once, Phobos has already gone around more than 3 times. This creates something that most moons in the solar system do not produce. Phobos, seen from the Martian surface, rises in the west, not the east, the west. It comes up where the sun goes down, where the stars move toward the horizon, and it travels across the sky in the opposite direction from everything else. And then it sets in the east. And if you're still awake, a few hours later, it rises in the west again and sets in the east again. 2 complete crossings of the Martian sky before a single Martian day is over. By the time the sun has risen once on Mars, Phobos has already crossed overhead, vanished, come back, crossed again, and is working on a 3rd passage. Think about what that means for a moment. Imagine sitting in the still dark of a Martian night, and it would be quiet and cold and breathtakingly starry, with no thick atmosphere to dim the heavens, and watching this small, rough-edged disk climb up from the west, move quickly overhead, and sink into the east in a matter of a few hours. Then watching it do it again. The motion would be quick enough to notice if you watched steadily. Not a streak, nothing alarming, just the clear and visible movement of a world going somewhere urgently. Everything else in the sky, the stars, the sun, the distant Deimos, drifts from east to west in the familiar way. Only Phobos comes the other direction. Only Phobos is in that much of a hurry. And because Phobos is moving so fast through its phases, if you watched on a clear night, you'd see it shift from a crescent to a gibbous shape and back again in just a few hours. The whole cycle of phases, new to full to new, takes less time than it takes for Mars to make half a turn. Phobos doesn't have the slow, patient monthly rhythm that our moon has. It is in constant, almost frantic change for a moon. A hurrying little world, lit and shadowed and moving and changing above a planet that barely seems to notice. And yet Mars does notice. Mars notices very much. Because Phobos is orbiting faster than Mars rotates, the tides that Mars raises on Phobos are pulling it forward, and then, this is the key thing, the slow-motion tragedy at the center of this little moon's existence, pulling it down. When a moon orbits faster than its planet rotates, the tidal bulge that the planet raises on the moon is always slightly ahead of the moon in its orbit, and the gravitational tug of that bulge acts like a brake. It slows the moon down very gradually, and a slower moon at that distance can't maintain the same orbit. It sinks. Millimeter by millimeter, year by year, century by century, Phobos is falling. Not in a dramatic way, not in a way you could watch. The fall is so slow it can only be measured by tracking Phobos's position over many decades and looking for the tiny shift. But it is real, and it has been confirmed, and it is relentless. Phobos is losing altitude at a rate of roughly 1.8 to 2 centimeters per year, the width of a few fingers, the length of a small key. Each year, Phobos ends up that much closer to Mars than it was the year before. Now 2 centimeters a year doesn't sound like much. And it isn't much, not in any human sense of timekeeping. Over a human lifetime, it adds up to perhaps 1.5 meters. Over all of recorded human history, a few thousand years, it adds up to a few dozen meters, the height of a modest building. Still not much, measured against 6,000 kilometers of altitude. But planets are old and time is patient, and 2 centimeters per year applied over tens of millions of years becomes something else entirely. In somewhere between 30 and 50 million years, the estimates vary and the uncertainty is honest and appropriate because these are complex systems we are modeling from the outside. Phobos will have fallen close enough to Mars that it crosses a threshold. That threshold has a name, the Roche limit. It is the distance from a planet inside of which the tidal forces pulling a moon apart becomes stronger than the Moon's own gravity holding itself together. Our Moon, much larger and more solid, would need to be 20 times closer to Earth than it is before reaching Earth's Roche limit. Phobos is already much closer to its Roche limit than most moons, and it is approaching it every single year. When Phobos finally crosses the Roche limit, when the pull of Mars's tides is finally stronger than the grip Phobos has on itself, what happens? There are two possible answers, and they are both beautiful in a quiet, distant way. The first possibility is that Phobos is torn apart, not explosively, not in a moment, but gradually and then more quickly, the Moon stretching and cracking along its weakest seams, loosing great chunks of rock that spread along its orbit, slowing and spreading and wrapping around Mars in a thin, wide arc. In this scenario, Mars would gain a ring, a faint one, a ring made of the broken body of its own closest moon, spreading into a bright band around the planet over thousands of years. Some researchers, including work published by Hesselbrock and Minton in 2017, have modeled exactly this outcome and found it quite plausible. Mars would join Saturn and Uranus and Neptune in having a visible ring, though Mars's would be smaller and fainter than any of theirs. And then, over millions more years, that ring would gradually decay. The particles would drift slowly inward and rain down onto Mars, a long, quiet meteorite shower, ending in the gentle arrival of Phobos, distributed across the planet's surface in tiny pieces over millions of years, not a crash, a slow dissolution, a moon becoming weather, becoming dust, becoming Mars. The second possibility is that Phobos survives long enough to actually strike Mars directly, that it holds together past the Roche limit, perhaps because it is more solid than we think, or the geometry works out differently, and then spirals all the way in. The impact, when it finally came, would be enormous. It would leave a crater hundreds of kilometers across. It would reshape the landscape of an entire region of Mars. But it would happen so far in the future that nothing we can currently imagine about the life of planets or the cooling of suns tells us what Mars would look like by then. Research published by Black and Mittal in 2015 worked through both scenarios carefully. The ring formation path looks, to many planetary scientists, like the more likely outcome. But the honest answer is that we don't yet know which it will be. We may not know until we understand Phobos's internal structure much better. Whether it really is a rubble pile, hollow in places, or whether it is solid rock throughout. And that brings us to a quality of Phobos that surprised the scientists who measured it carefully. Phobos is lighter than it should be. When the European Space Agency's Mars Express spacecraft flew very close to Phobos, sometimes within tens of kilometers of its surface, tracking the gravitational tug Phobos exerted on the spacecraft to an extraordinary degree of precision. The measurements came back telling a strange story. The mass of Phobos is much lower than the volume of Phobos would suggest if that volume were full of solid rock. The density of Phobos works out to about 1.86 grams per cubic centimeter. Solid rock, the kind that makes up our own moon, and the surfaces of the inner planets is typically 2.5 to 3 grams per cubic centimeter or more. Water is 1 gram per centimeter. Phobos, at 1.86, sits in an uncomfortable middle zone. That low density means something is making Phobos lighter than solid rock should be. There are two leading explanations, and they are not mutually exclusive. The first is that Phobos is porous, full of empty spaces, cracks, and voids, perhaps a jumbled collection of rocks only loosely held together by its own faint gravity. This is what planetary scientists call a rubble pile, and it is a structure we see in some asteroids. A rubble pile that has been compressed very slowly over billions of years, with the gaps between its constituent rocks accounting for the missing mass. The second explanation is that some of that interior volume is occupied by something lighter than rock. Water ice, perhaps, or carbon compounds. Not a lot of it, but enough to bring the average density down. Mars Express's measurements could not tell the difference between these two possibilities from the outside. The only way to know would be to go inside or to analyze the surface material directly. This is part of why the coming mission matters so much, but we'll get to that a little later. For now, let's look at Phobos more closely. Specifically, let's look at the wound. On the surface of Phobos, there is a crater. You already know its name. Stickney. It was named, as Hall's other honors went, for Angeline Stickney, the woman who told her husband not to give up the search. And the naming here feels almost weightier than usual because Stickney Crater is not a small feature on a small moon. It is a defining feature. It is nearly half the size of the entire moon. Stickney Crater is about 9 kilometers wide. Phobos at its largest is about 27 kilometers across. So Stickney takes up nearly half the width of one face of the moon. If you could hover above Phobos and look down at it, Stickney would not be a blemish. It would be a wound that dominates the entire view. A deep, bowl-shaped hollow with terraced walls slumped and collapsed inward, with its floor cratered again by smaller, later impacts that have added their own marks over the billions of years since the original blow. Inside Stickney, sitting on its floor, there is a smaller crater named Limtok, a crater within a crater. Impacts upon impacts, time layered on time, in miniature. Mars Express captured images looking almost straight down into Stickney from very close, and those images show the terraced, slumped walls, the uneven floor, the smaller craters nested inside. It is a view of something very old and very quiet. But here is what the Stickney impact means for Phobos beyond just the crater itself. When something strikes a body in space hard enough to make a 9-kilometer crater, hard enough that the crater is half the size of the body it's punched into, the forces are not contained neatly within that one spot. The energy of the impact sends shock waves racing through the whole body. And those shock waves, in a body as small as Phobos, do not have far to travel before they find no more material to pass through. The energy has nowhere to go but back. Planetary scientists who have modeled the Stickney impact believe the event nearly shattered Phobos. Not cracked it in one place, shattered it, nearly broke it apart entirely. The fact that Phobos exists at all is perhaps testimony to how tightly, or how loosely, its material held together under that enormous stress. Whether Phobos is solid or a rubble pile, it absorbed a blow that came very close to being the last blow it would ever receive. And then there are the grooves. Running across the surface of Phobos, photographed first by the Viking orbiters in the 1970s and then in greater detail by Mars Express, are long parallel striations. The NASA term for them is simply grooves. They are channels, ruts, and shallow furrows crossing the surface in sets, many of them remarkably parallel to one another, running for kilometers across the little moon's face. Some of them are a few hundred meters wide and tens of meters deep. They are one of the first things you notice in any photograph of Phobos. Something has marked this moon heavily, and not just with impact craters. The question of what made the grooves is not fully settled, but there is one idea that connects back directly to Stickney, and it is perhaps the most unsettling. Some of the grooves appear to radiate outward from Stickney, or at least to align with directions consistent with the shock of the original impact. In this interpretation, the grooves are early fractures, stress cracks that formed in the body of Phobos when the Stickney impact sent its shockwaves through the moon. The grooves in this reading are the first signs of a slow-motion breakup that began billions of years ago and has not finished yet. They are the cracks already showing in a thing that is falling apart very, very slowly. Other researchers have proposed that the grooves are not internal cracks but external features. Lines of small craters formed when debris ejected by some other impact elsewhere in the solar system came raining back down in long chains. or when boulders rolled across Phobos's dusty surface and left trails in the regolith. The debate is not over. There are good arguments on multiple sides, but the fracture crack interpretation is the one that gives the grooves a connection to the larger story of Phobos's eventual fate. A moon already cracking under the tidal pull of a planet it orbits too close to, striped with the marks of nearly dying before it has actually died, falling slowly toward the end that the physics always promised. And there is one more observation worth resting on for a moment before we leave the subject of the grooves. Mars Express has confirmed by its gravity measurements that Phobos is underdense, that rubble pile or porous interior we just talked about. A rubble pile is much more vulnerable to tidal disruption than solid rock would be. A rubble pile can be pulled apart by tidal forces at distances where solid rock would remain intact, which means that if the rubble pile interpretation is correct, Phobos may cross the Roche limit sooner than models based on solid rock would predict, and it may break apart more dramatically when it does. The grooves as fractures, the low density as fragility, the Stickney impact as the wound that may have already started the process. They all point in the same direction. Phobos is a world that has been in the process of ending for a very long time. The inward drift was first confirmed not by a single observation, but by patient accumulation. Scientists tracked the position of Phobos across decades of measurements, Viking data, then later spacecraft, then Mars Express, and compared where Phobos was to where the orbital calculations predicted it should be if nothing were changing. Phobos was consistently slightly ahead of where a stable, non-decaying orbit would put it. Ahead because as it spirals inward, the orbital period gets shorter, the moon goes around faster, and it arrives at any given position in its orbit a little earlier each year. That tiny accumulated lead in position is the signature of a falling orbit, confirmed again and again across decades of watching. Phobos is not falling in a way that could be seen on human timescales, but it is falling in a way that physics demands and patience reveals. So we have a picture now of Phobos in its full strangeness, closer to its planet than any other moon in the solar system, orbiting in 7 hours and 39 minutes, faster than Mars can rotate, rising in the west, moving backward across the sky, setting in the east, and doing it all again before the Martian day is over. Scarred by a crater nearly half its own size, scored by grooves that may be stress fractures of a long, slow breaking, underdense, perhaps hollow, or mixed with something lighter than rock. Losing 2 centimeters of altitude per year? Falling. Angeline Stickney told her husband not to give up, and he found this. A doomed, scarred, backward, hurrying little world that carries her name in its greatest wound and will carry it in some scattered form for tens of millions of years more until the planet finally calls it home. Now settle in a little more. We're going to move from the falling moon to the one that is leaving. Deimos is different in almost every way that matters, and the contrast between the two moons is one of the quietest and most satisfying things about this little system. Where Phobos is low and fast and scarred and falling, Deimos is distant and slow and smooth and drifting away. The same planet made 2 moons, or captured them, or both, though we'll come to that, and gave them opposite destinies. Fear tumbles inward. Dread slips outward. Both moving, both changing, across timescales too long for any individual life to witness, but real and confirmed and measurable. Deimos orbits about 23,460 kilometers from the center of Mars. Put that next to Phobos's 9,376 kilometers and feel the difference. Deimos orbits nearly 2.5 times farther from Mars than Phobos does. It lives in calmer, more spacious territory, and its period reflects that distance. Deimos takes about 30 hours and 18 minutes to complete one orbit. 30 hours and 18 minutes compared to Phobos's 7.5. A slow, measured thing. That orbital period is just slightly longer than a Martian day, and this fact changes everything about how Deimos looks from the Martian surface. Because Deimos orbits just a little slower than Mars rotates, Deimos appears to move in the conventional direction, rising in the east, setting in the west, just like the sun and the stars. But it moves so slowly that it barely seems to move at all. An observer watching Deimos from the surface of Mars would see it rise in the east and spend about 2.5 days crossing the sky before it finally set in the west. 2.7 days from rising to setting for a single crossing. During that time, Deimos would go through its full cycle of phases slowly and visibly, waxing and waning over nearly 3 Martian days. It would be a leisurely, gentle presence in the sky, not the frantic backward rush of Phobos, but a slow, companionable drift. From the surface of Mars, Deimos would not look like a disk in any obvious way. It would look like a very bright star. Its angular size, seen from Mars, is small enough that to the naked eye it would resemble Venus as seen from Earth. A brilliant, steady point of light, noticeably brighter than most stars, but not a disk, not a shape. You would know it was a moon by its motion and its phases, not by any visible face. Phobos, by contrast, would clearly be a disk, roughly 1/3 the angular diameter of our full moon as seen from Earth, large enough that you could tell it was a solid body, large enough that under good conditions you might, as mentioned, just barely make out the shadow of Stickney as a darkening on its surface. But Deimos would be a point, a slow, wandering, bright point. The surface of Deimos is different from Phobos's in texture and appearance. Where Phobos is heavily grooved and heavily cratered, with a rugged, marked surface that tells a violent history, Deimos looks smoother, not because it has been struck less. Both moons have been bombarded by micrometeorites and debris over billions of years, but because Deimos is covered in a thick layer of fine regolith, that dusty, powdery blanket of crushed rock that accumulates on airless surfaces everywhere in the solar system. On Deimos, this layer appears to be especially deep and especially fine, filling in impact craters and smoothing over the sharper features that might otherwise show. Viking and Mars reconnaissance orbiter images both show a surface that looks almost upholstered compared to the scarred, grooved face of Phobos. Softer looking, more muted, the two largest named craters on Deimos are Swift and Voltaire. Not enormous features, Deimos is a smaller world, but named deliberately, as we've already talked about, for the writers who imagined Mars's moons into existence before anyone had seen them. Swift sits on one part of Deimos's surface, Voltaire on another. If you were standing on Deimos and could find them underfoot, you would be standing on the names of two men who told a story that, by the strangest luck, turned out to have the right outline. There is a gentle irony in the fact that the craters were probably made by impacts that had nothing to do with literature or whimsy, just random rocks arriving from the darkness. And yet, the names they carry now are some of the most human names in the solar system. Deimos's gravity is extraordinarily faint. It is a small body, and small bodies have little mass. And little mass means little gravitational pull. The escape velocity from the surface of Deimos, the minimum speed you would need to throw a rock in order for it to leave Deimos entirely and not fall back, is about 5.6 meters per second. That is roughly 20 kilometers per hour. A fast cyclist could reach that speed. A good throw by an athlete could send a ball off Deimos forever. You would not need a rocket, you would not need any equipment at all beyond a strong arm and a well-aimed stone. The rock would arc away from the surface, climbing slowly, then continuing to climb because there is not quite enough gravity to bring it back, and eventually disappear into the darkness between Deimos and Mars to drift in its own slow orbit, or eventually fall somewhere else, carrying no particular story with it. And yet, despite this almost absurdly gentle gravity, Deimos holds together. Its regolith stays on its surface. Its shape, irregular and lumpy at 15 by 12 by 11 kilometers, persists. Gravity is weak, but it is not nothing, and over geological time, it is enough to keep the dust from simply drifting off into space, mostly. There is actually a very faint cloud or torus of dust that seems to travel with Deimos along its orbit, shed from its surface by the constant light tapping of micrometeorites. But this dust is so sparse it is essentially invisible. It is detected by instruments, not by eyes. This is the quiet difference between the two moons' fates. Phobos is below the synchronous orbit, and so Mars's tidal gravity drags it inward. Deimos is above the synchronous orbit, just barely above in cosmic terms, and so Mars's tidal gravity pushes it outward. The same force, working in two different configurations, produces two opposite results. One moon falls, one moon climbs. Our own moon is in exactly Deimos's position relative to Earth, above synchronous orbit, being pushed away by tidal forces, retreating from us by about 3.8 centimeters per year. Deimos's outward drift is slower, much slower, because Deimos is so small and tidal forces scale with the cube of the distance and the mass of the bodies involved, but it is moving in that same quiet outward direction. Where Phobos's fate is sealed, it will end one way or another at Mars. Deimos's future is more open. It may drift outward indefinitely, growing ever more slowly with each passing era, the tidal push getting weaker as the distance grows, until eventually the force becomes so negligible that Deimos simply settles into a stable orbit and stays there, perhaps forever. Or, and this is less certain, more speculative, if it drifts far enough and slowly enough, and if the gentle gravitational nudges of the Sun and Jupiter become significant over the very longest time scales, Deimos might one day be nudged loose from Mars's gravity entirely. It might escape. It would become an independent body, a small asteroid drifting in the inner solar system, carrying its craters and its regolith and its names, Swift and Voltaire, into the wider darkness. We don't know which of these endings awaits Deimos. The timescales are too vast for certainty, and the models depend on assumptions about Mars's internal structure and the long-term stability of the solar system that are themselves uncertain. But the general shape of Deimos's future is away, out, quietly, unspectacularly, like a companion who steps back from a doorway without making a scene. Fear falls, dread walks away, and we are left with a planet between them, Mars, ancient and red and thin atmosphered, orbiting the Sun on its own longer schedule, a planet that has two moons now but may, in the fullness of time, have none. First, it will briefly have a ring, the broken body of Phobos spread thin and beautiful and temporary around its equator, glittering faintly in the weak Martian sunlight. And then even that will settle, grain by grain, onto the surface. And Deimos will have gone on. And Mars will be alone, as it was for most of the billions of years of its history before these two small things arrived or formed, however they arrived or formed. But we still don't know which it was. That mystery has not been solved yet. And it is one of the genuinely open questions of planetary science, not a matter of settled consensus with only the details left to fill in, but a real and active debate. So let's rest in it for a moment, because unsettled questions explored gently and honestly are some of the most interesting places to spend a quiet hour before sleep. The first question is, where did these two small lumps of rock come from? And the honest answer, even now, even after decades of telescopes and orbiters and flybys and careful spectrometry, is that we genuinely do not know. The origin of Phobos and Deimos remains one of the quietly open problems of our solar system. Not open in the way that a question is open, when everyone suspects the answer, but is waiting on the final proof. Open in the deeper way, where multiple plausible explanations each have real evidence behind them, and the experiments needed to distinguish between them have not yet been done or have not yet returned from wherever they are traveling. That uncertainty, if you let it, is actually a rather comforting thing to sit with before sleep. The universe is not fully catalogued. The two moons closest to us in the night sky, the ones orbiting our nearest planetary neighbor, still hold their origins like a private secret. There is something almost courteous about that. So let's move through what we do know and what we suspect, and where the debate lives. The first thing to understand about Deimos before we talk about where it came from is simply where it is. Deimos orbits Mars at a distance of about 23,460 kilometers from the planet's center. That is much farther out than Phobos, which, as we've been talking about, huddles only about 9,376 kilometers from Mars's center. Deimos has room. Deimos has space around it. If Phobos is a moon that is almost too close, crouched low and circling frantically, then Deimos is the one that has given itself a little distance, that orbits with something closer to patience. It takes Deimos about 30 hours and 18 minutes to complete one full circle of Mars, just over a Martian day. And this single number is the reason Deimos behaves so differently in the Martian sky than Phobos does. You remember that Phobos, because it races around Mars faster than Mars itself, rotates, rises in the west and sets in the east, everything backward, everything hurrying. But Deimos orbits at just about synchronous altitude, just barely outside the distance at which a moon's orbital speed would match Mars's rotation. Because it is just a little farther out than synchronous orbit, it moves just a little more slowly than the Martian ground beneath it. So Deimos rises in the east and sets in the west, the same direction as the sun, the same direction as the stars. Normal, ordinary, but so slow. From the surface of Mars, Deimos would take roughly 2.5 to 2.7 days to cross from one horizon to the other. You would watch it rise in the east. You would see it move, if you watched carefully, over hours. By the time it set in the west, more than 2 days would have passed. It is barely moving from the perspective of someone standing on Martian soil, like watching a very slow ship cross a very calm sea. During that long crossing, Deimos would go through its phases, waxing from crescent to full and back to crescent again, but stretched across those 2.5 days rather than the hours Phobos takes. Its size in the sky would be small. From Mars, Deimos would look more or less like Venus looks from Earth, a bright and steady point of light, noticeable but not dramatic, not a disk you could see with the naked eye as a disk, not a presence that fills a quarter of the sky, just a bright, slow-moving star that sometimes shows a faint crescent if you look closely. There is something peaceful about that. A small, bright, patient light drifting through the Martian night over the course of days, not rushing, not looping, just moving, now on its surface. If you could somehow set down on Deimos, the first thing you would notice is how smooth it looks compared with Phobos. Not featureless, exactly. There are craters, some quite old and battered, and the surface is covered in regolith, that blanket of powdered and shattered rock that builds up wherever micrometeorites have been striking a body for billions of years. But the craters on Deimos are filled in more than they are on Phobos. The fine dust and rubble have settled into them, blurring their edges, making the whole surface look softer, less jagged, less tortured. Phobos shows you its violence. The grooves, the shattered crater rims, Stickney like a wound. Deimos keeps its history a little more hidden under dust, a quieter face. The two largest named features on Deimos are both craters, and their names bring us back to those literary predictions we talked about earlier. One is called Swift, and the other Voltaire, named, as you might remember, for Jonathan Swift, who in 1726 wrote into his satirical novel Gulliver's Travels a fictional account of astronomers on the flying island of Laputa who had discovered two small moons orbiting Mars, and for Voltaire, who in his 1752 story Micromegas mentioned those same two moons. Both writers died without knowing they had accidentally named something that was real. The International Astronomical Union placed their names on the very object they had imagined, and now those names travel around Mars on the surface of Deimos, quiet memorials to a strange literary coincidence. There is one more fact about Deimos that gives a sense of just how small and lightly gravitated it is. The escape velocity on Deimos, the speed at which something must be moving to leave the moon entirely and never fall back, is only about 5.6 meters per second. That is roughly 20 kilometers per hour. Not much faster than a brisk bicycle ride. A good athlete could, in principle, throw a rock fast enough to send it off Deimos forever, sailing away into space. You would not need a rocket. You would need an arm and a clear aim and a moment of perhaps excessive enthusiasm. That rock would drift off into the Martian system, never to return. That is how small Deimos is. That is how gently it holds things. And so Deimos drifts. It orbits just beyond the synchronous radius, and so Mars's tidal forces, rather than pulling it inward the way they pull Phobos, are very slowly nudging it outward. Just as our moon, which also orbits beyond Earth's synchronous radius, is slowly receding from us at a few centimeters per year, Deimos is slowly receding from Mars. The motion is tiny, the timescales are immense, but the direction is clear. Away. Whether Deimos will eventually drift far enough to escape Mars's gravity entirely and become a small, independent body wandering the solar system is not certain. The models suggest it is possible, but the timeframes are so vast and the influences so many that confident prediction becomes difficult. What we can say is that the trajectory is outward. Deimos is the moon that is leaving, fear and dread. One falls, one walks away, but back to the question of where they both came from. The oldest, and in many ways, still the most intuitive idea is that Phobos and Deimos are captured asteroids. Wanderers from the asteroid belt, that broad region of rocky and metallic debris that stretches between Mars and Jupiter, caught long ago by Mars's gravity and pulled into orbit. There is some appealing evidence for this. The surfaces of both moons are dark, reflecting only about 6 or 7% of the sunlight that falls on them. That is an unusually low reflectivity, and the color and spectrum of that dark surface, the mix of wavelengths they reflect and absorb, resembles quite closely a class of asteroids called D-type asteroids, sometimes also described as carbonaceous, meaning they are rich in carbon-bearing primitive material that has changed very little since the solar system formed. This is old stuff, ancient stuff, the same kinds of molecules that appear in the most ancient meteorites that fall to Earth. So in terms of what they look like, Phobos and Deimos do look a little like asteroids. That is a point in the capture story's favor. But here is where the problem comes in. If you capture an asteroid, you capture it by having it pass close to a planet and get slowed down enough to be trapped. The trouble is that the physics of capture almost always leaves the new moon in an orbit that is tilted and elongated, elliptical rather than circular, maybe inclined at a strange angle relative to the planet's equator. Capture is a messy, chaotic process. It does not typically produce neat, tidy orbits. And the orbits of Phobos and Deimos are almost suspiciously neat. Both moons orbit very close to the plane of Mars's equator. Both orbits are nearly circular. This is not what you would expect from captured asteroids that arrived from random directions. Getting two asteroids captured into orbits that are both nearly circular and both nearly equatorial would require a remarkable coincidence, or some additional process, that circularized and flattened the orbits after capture. Such processes exist, but they add complexity to the story. The more steps you need to explain something, the more you have to wonder whether there is a simpler explanation. And there is another. The competing idea holds that Phobos and Deimos are not visitors at all, but children of Mars, that they were born from material blasted off Mars itself long ago by a giant impact. Early in the solar system's history, large impacts were common, the same kind of event that, according to the prevailing theory, created our own moon by smashing a Mars-sized body into the early Earth and throwing a cloud of debris into orbit. Something similar could have happened to Mars. A large object strikes Mars. An enormous amount of material is blasted into orbit. That material forms a disk. Over time, the disk coalesces into one or more moons. The moons start out close to Mars and some drift outward, settle, stabilize. If this is what happened, then Phobos and Deimos are partly made of Mars. They carry Mars inside them, material from the planet's crust and mantle, mixed with whatever struck it. They would not be outsiders, they would be family. The researchers Rosenblatt and Craddock, working independently and with collaborators, have developed models in this general direction, exploring how a disk of impact debris might produce moons with the orbital properties we observe. The circular equatorial orbits are naturally explained if the moons formed from a disk that settled along Mars's equatorial plane. Impact-borne moons would form there, would stay there. They would not need to have their orbits reshaped after the fact. And then there is a third idea, which adds another layer of strangeness and, in my opinion, a certain quiet elegance. The work of Hesselbrock and Minton, published in 2017, proposed something called the cyclic moon model. The idea is roughly this: Mars may once have had a larger moon, or perhaps several moons over its history. Those moons, if they were close enough, would have been pulled inward by the same tidal forces that are now pulling Phobos inward. They would have reached the Roche limit, the distance from Mars at which tidal forces overcome the moon's own gravity and begin to tear it apart. They would have broken up, spreading their material into a ring around Mars. That ring would then slowly rain down onto Mars, partly, while another part might gather at the edges and coalesce into a new, smaller moon. That new moon would itself be pulled inward, would itself eventually break up into a ring, and the cycle would repeat. Over billions of years, Mars could have had a sequence of moons, each one a little smaller than the last, each one born from the rubble of the previous, each one living its life and falling and becoming a ring, and then the ring becoming a new moon again. Under this model, Phobos might not be the first Martian moon, but the latest in a long line of them. It carries, perhaps, not just its own history, but echoes of older moons that no longer exist, material from bodies that lived and fell and were reborn again and again over the deep time of Mars's existence. It is a rather extraordinary image if you sit with it. Mars surrounded by a succession of small, temporary moons, each one descending, each one being torn apart and spread into a brief, glittering ring, and then the ring coalescing and beginning the process again. A planet that makes moons the way a wave makes foam, repeatedly, the same general shape appearing and disappearing over geological time. We do not know which of these stories is the true one. Captured asteroid, impact-born children of Mars, or the latest members of a recycled lineage born from rings and doomed to become rings again. All three ideas have adherents, all three have supporting evidence, all three have difficulties. The question is genuinely open, but something is coming that might finally answer it. Japan's space agency, JAXA, is developing a mission called MMX, which stands for Martian Moons Exploration. The plan is to send a spacecraft to the Martian system, study both moons in detail, and then land briefly on Phobos and collect a sample of its surface. At least 10 grams of material, small enough to fit in your palm, brought back across the distances of the solar system to Earth's laboratories. That sample is the key, because if you can analyze the actual chemical composition of Phobos's surface material in detail, you can compare it to the chemistry of known asteroid types and to the chemistry of Mars itself, the Mars we know from Martian meteorites that have fallen to Earth. If Phobos is a captured asteroid, its material should look like asteroid material, not like Mars. If Phobos was born from a giant impact, its material should contain signatures of the Martian crust or mantle mixed in with whatever struck. The chemistry should tell the story. It would be the first time any material from a moon of Mars has ever been returned to Earth. If it arrives and is analyzed, it may resolve in a few months a question that has been debated for decades. MMX also carries a small rover contributed by the German Space Agency (DLR) and the French Space Agency (CNES). That rover, called ID-FIX, is designed to roll across the surface of Phobos in its extraordinarily low gravity, taking measurements, exploring the terrain, looking at the texture and composition of the surface up close in ways that orbital observations cannot provide. A little wheeled machine wandering across a body only 27 kilometers long, the gravity so weak that a careless turn could send it drifting off the surface entirely. And there is another possibility that makes the MMX sample even more scientifically rich, and which connects back to the giant impact hypothesis. If Phobos was formed from material blasted off Mars by a large impact, then some of that material might include pieces of ancient Martian rock from the planet's early history, billions of years ago, when conditions on Mars were very different from what they are today. Mars is thought to have had liquid water on its surface in its early history, a thicker atmosphere, perhaps conditions that were, in some ways, less hostile than they are now. Pieces of that early Mars, sealed inside Phobos for billions of years and then returned to Earth, could carry chemical and mineralogical evidence of what Mars was like in its first chapter. You might learn something about ancient Mars from a moon of Mars rather than from Mars itself. The moons as archives, the moons as libraries, holding records that the surface of Mars, constantly reshaped by wind and dust and occasional geological activity, might no longer preserve as clearly. That is what is waiting, depending on how MMX unfolds. Now let's spend a little time with the history of how we came to know what we know about these two small bodies, because the story of their exploration is, in some ways, as interesting as the moons themselves. It begins in 1971 with a spacecraft called Mariner 9. Mariner 9 was the first spacecraft to orbit another planet. It arrived at Mars in November of 1971, and after waiting out a global dust storm that briefly obscured the Martian surface, it began mapping and imaging everything it could see. That included, for the first time, close-up views of Phobos and Deimos. The first images were not detailed enough to reveal much surface texture, but they confirmed the basic shapes, confirmed that these were irregular, lumpy bodies rather than spheres, and gave the first rough sense of their sizes and surfaces. Before Mariner 9, almost everything known about Phobos and Deimos had come from Earth-based telescopes, where they appeared as nothing more than tiny, faint points of light. After Mariner 9, they began to become places. Then came the Viking orbiters in the late 1970s. The Viking mission sent 2 landers to the Martian surface and 2 orbiters to circle Mars from above, and those orbiters gave us the first detailed maps of both moons. Viking images resolved individual craters, revealed the grooves on Phobos, showed the terraced walls inside Stickney, and gave enough coverage of Deimos to see the softer, dust-filled texture of its surface. These were the images that defined both moons for a generation of planetary scientists and curious observers. The 1980s brought an attempt at something more ambitious. The Soviet Union, then still in existence as a spacefaring power, planned a pair of dedicated missions to Phobos, named, straightforwardly, Phobos 1 and Phobos 2. Both launched in 1988, aiming to orbit Mars, study Phobos in detail, drop landers onto its surface, and conduct a range of experiments. It was an ambitious program, and the plans were detailed and scientifically promising. Phobos 1 never made it. A faulty command sent from the ground during routine operations on the way to Mars accidentally switched off the spacecraft's attitude control thrusters. The spacecraft lost its orientation, could no longer point its solar panels at the sun, lost power, and went silent. It was a small human error, a sequence of wrong characters in a command string, and it ended the mission before Mars was even in sight. Phobos 2 did better. It reached Mars orbit and began conducting observations, sending back data about the Martian environment and capturing some images of Phobos from a distance. It was on its way to a close approach of Phobos, the approach it had been sent so far to make, when contact was lost. The last data was received in March of 1989. The cause was never fully determined, a possible failure in the onboard computer, a possible electronics problem. The spacecraft was silent, and the close approach never happened. Some of the science was retrieved from the data Phobos 2 had already sent back, but the mission's central goal, the close-up study of the Moon itself, was not achieved. Then, more than 2 decades later, Russia tried again. The Phobos Grunt mission, launched in November 2011, was designed to do something even more ambitious than its predecessors: land on Phobos, scoop up a sample of its surface, and return that sample to Earth. If it had worked, it would have been the first sample return from any body beyond the Earth-Moon system since the Apollo era. The mission also carried a small Chinese spacecraft, Yinghuo 1, intended to study the Martian atmosphere and environment. Phobos Grunt never left Earth orbit. After launch, the spacecraft failed to fire its engines for the burn that would have sent it on the long journey toward Mars. It sat in a low Earth orbit, circling the planet silently, its engines stubbornly inert. Ground teams tried for weeks to regain control and rescue the mission, sending commands, attempting to reboot systems, hoping for some response. None came. In January 2012, Phobos Grunt and the Chinese Yinghuo 1 spacecraft re-entered Earth's atmosphere and burned up. An extremely ambitious mission, years in the planning, ended without having traveled more than a few hundred kilometers above the planet it was launched from. These failures are not just footnotes. They speak to how difficult it is to reach Mars, and specifically to reach the moons of Mars and to conduct close-up science there. Every successful mission that has returned useful data from Phobos or Deimos represents not just scientific achievement but also the overcoming of extraordinary engineering challenges over hundreds of millions of kilometers of space. The successful ones have been remarkable. Europe's Mars Express spacecraft, which has been orbiting Mars since 2003, has conducted some of the most detailed close studies of Phobos ever performed. Mars Express has made many flybys of Phobos, sometimes passing within a few tens of kilometers of the surface, close enough that the Moon's gravity measurably perturbed the spacecraft's trajectory. By precisely tracking those tiny perturbations, the tracking stations on Earth could work out the mass of Phobos with great accuracy, and from the mass and the known volume, calculate the density. And that density, about 1.86 grams per cubic centimeter, was a surprise. It is lower than you would expect for solid rock, much lower. It means that Phobos cannot be a uniform ball of rock. Either it has empty spaces inside, pores and voids and cavities, like a rubble pile loosely held together rather than a solid body, or it contains significant amounts of less dense material, perhaps ice, perhaps a large amount of carbon-rich, low-density minerals, or some combination of both. The rubble pile interpretation has become rather popular among planetary scientists, and it has an interesting consequence for Phobos's future. A rubble pile is not a monolith. It is a collection of pieces held together by their own very weak mutual gravity. When tidal forces from Mars finally become strong enough to disrupt Phobos as it gets closer and closer, a rubble pile might respond quite differently from a solid rock. It might begin to shed material early, gradually, as the outer layers are pulled free first. The breakup might not be a single catastrophic shattering, but a slow unraveling piece by piece the rubble gradually dispersing into a ring while some central remnant persists a little longer, which is its own kind of ending, quiet and gradual, like the slow dissolution of something that was never completely solid to begin with. Mars Express has also given us detailed imaging of Phobos, revealing the surface texture, the groove structures, the shape of Stickney, and its inner crater Limtok, with a clarity that the earlier Viking observations could not quite achieve. And then there is HiRISE, the high-resolution imaging science experiment, the powerful camera aboard NASA's Mars Reconnaissance Orbiter, which has been in Mars orbit since 2006. HiRISE is not primarily designed to look at the moons, but it has turned its exceptionally sensitive eye toward Phobos on multiple occasions, and some of what it has shown is striking. In particular, color images taken by HiRISE reveal that Phobos's surface is not uniform. Most of it is a reddish-brown, the color of ancient space-weathered rock, exposed for billions of years to the gentle but relentless bombardment of solar wind particles and micrometeorites that slowly alter the chemistry of exposed surfaces in a process called space weathering. But the region in and around Stickney crater appears noticeably bluer in these color images. The interpretation is that the material exposed by the Stickney impact is fresher. It was buried beneath older, weathered surface material, and the impact blasted it into view relatively recently, geologically speaking. The blue color represents unweathered, relatively pristine rock, less altered by the space environment because it has been exposed to it for less time. Stickney's blue tinge is, in a sense, a window into Phobos's interior, or at least into slightly deeper layers of its surface. Younger material, fresher material. The scar that nearly killed the moon also, in a strange way, revealed something of what is inside it. And then there are the rovers on the Martian surface. Curiosity, which has been exploring Gale Crater since 2012, and Perseverance, which arrived at Jezero Crater in 2021, have both captured something rare and lovely: Phobos crossing in front of the Sun. Because Phobos is so small, it does not create a total solar eclipse as it passes between Mars and the Sun. It cannot cover the entire solar disk. What it creates is a partial eclipse, a transit, a dark silhouette of Phobos's irregular, lumpy shape moving across the bright circle of the Sun. The rovers have captured these events on camera, watching Phobos take a bite out of the Sun and then move on, the whole event lasting only about 30 seconds, because Phobos is moving so quickly across the sky. 30 seconds of partial darkness, a shape like a lumpy potato, sliding briefly across the face of the Sun as seen from Mars. These images are wonderful for their own sake, a small moon making a small eclipse on a distant planet witnessed by a machine the size of a car sitting in an ancient lakebed or crater, sending the images back across hundreds of millions of kilometers to curious human beings who built it. But they are also scientifically useful. By timing these transits very precisely and by comparing the timing with the predictions based on orbital models, scientists can detect tiny discrepancies that reveal information about Phobos's exact orbital position. The shadow of Phobos racing across the Martian ground, photographed from the ground at the same moment, allows the orbit to be refined to extraordinary precision. A small moon making a small eclipse, and in doing so telling us more precisely where it is and therefore how fast it is falling. That is what exploration has looked like for the moons of Mars. A sequence of missions stretching from Mariner 9 in 1971 through the Viking orbiters, the Phobos missions with their heartbreaking failures, Mars Express with its patient close passes, HiRISE with its color revelations, and the rovers on the ground looking up. Each mission adding something to the picture, each mission asking questions that the next one or the one after that will try to answer. And now MMX is being prepared, and when it arrives and when it lands its brief landing on Phobos, and when it collects its small handful of surface material, and when it begins the long journey back, it will be carrying something that no one has ever carried before from that part of the solar system. the actual substance of a Martian moon lifted off its surface and brought home. The sample will be small. 10 grams is not much, but 10 grams from Phobos, studied in the best laboratories on Earth with techniques that could not be carried to Mars and could not be conducted remotely from orbit, will be enough. It should be enough to identify the minerals, to date the rock, to look for signatures of Mars itself, if they are there, to look for signs of primitive asteroid material, if that is what it is instead. And so the question hangs open a little longer, gently, as questions do when we have not yet done the thing that would answer them. We know a great deal about these two small moons, more with every passing decade. But the central mystery of their birth, the question of whether they are captured wanderers or children of Mars, or the latest generation of a long cycle of destruction and renewal, remains for now beautifully, honestly unresolved. Which is, when you think about it, a good place to be before sleep. Uncertainty has a different quality than ignorance. Ignorance is not knowing and not knowing what you are missing. Uncertainty is not knowing but knowing the shape of the question, knowing what you would need to find out, knowing that someone or something is on its way to answer it. Uncertainty is a door that is closed but not locked. MMX is the key, traveling slowly through space toward a small, lumpy moon whose origin is still a secret. And when it arrives, and when it gets its 10 grams, and when it comes home, we will open that door. For now, both moons keep their secret. Phobos falling, Deimos leaving. Both born somehow from the early chaos of a solar system that is now more than 4.5 billion years old. Both carrying their craters and their regolith and their faint, dark surfaces through the Martian sky, one hurrying and one patient, both indifferent to the question we are asking about them. And the question is asked, and the mission is prepared, and in the meantime the two moons go on orbiting in their quiet and ancient and slightly mysterious way, as they have done for a very long time, and as they will do for a little while longer. And that is where we leave the mystery for now and turn toward something a little more tactile, something closer to the question of what it would actually mean to go there. Japan's space agency, JAXA, has been preparing for years a mission called MMX, Martian Moons Exploration. The name is precise and the ambition is large. The plan is to send a spacecraft all the way to the Martian system, study both moons in close detail, and then do something that has never been done before with any moon of Mars, land briefly on Phobos and bring a piece of it home. Not a large piece. The goal is at least 10 grams of surface material. 10 grams is about the weight of 2 nickels. 2 nickels worth of ancient, dark, dusty regolith from a moon that orbits 6,000 kilometers above the surface of Mars. And yet those 10 grams could change everything we think we know about where Phobos came from, and by extension where Deimos came from, and perhaps even something about the early history of Mars itself. Because if Phobos is what the giant impact models suggest, if it is made partly of material blasted off Mars by a collision long ago, then a sample of its surface is not just a sample of Phobos. It is a sample of Mars as Mars was billions of years before any spacecraft ever visited. The ancient surface, the early crust, material from a time when the planet was still warm and geologically active, and possibly, in some form, wet. That story is locked in those 10 grams, or it isn't. But until we open the box, we simply don't know. The sample return is the heart of the mission, but MMX carries more than a collection device. It carries a small rover built through a collaboration between the German space agency DLR and the French space agency CNES. The rover has been named IDFix, a nod to a small but fiercely loyal character in a beloved European comic, which feels rather fitting for a small but important machine being sent to one of the smallest significant moons in the solar system. IDFix is designed to roll across Phobos' surface in that almost non-existent gravity, measuring, photographing, and recording the landscape of a world where no wheel has ever turned. Think about that image for a moment. A little rover, no larger than a suitcase, rolling slowly across the surface of Phobos. The ground beneath it is dark and fine and ancient, the regolith built up over billions of years of micrometeorite rain. There is no air, there is no sound. The sky above is black, even in full sunlight, because there is no atmosphere to scatter light into a blue dome. Mars hangs enormous in that black sky, filling a huge arc of the view, its russet and ochre surface close enough to see in detail without any telescope at all. And IDFix rolls quietly across a few meters of this extraordinary ground, its instruments recording what no instrument has recorded before. That is the plan. That is what MMX is for. And depending on what it finds, in the spectrum of the soil, in the ratios of different isotopes locked in those 10 grams, we may finally close one of the oldest open questions in the study of the Martian system. Captured asteroid or child of Mars or something in between? The answer is out there, in the dark, on a lumpy little moon that has been keeping its secret for 4.5 billion years. For now, though, let's leave the spacecraft in their trajectories and their preparation rooms and their clean assembly facilities and do something perhaps more personal. Let's go there in imagination. Let's think about what it would actually feel like to stand on Phobos. The first thing you would notice before anything else is the gravity, or rather the near-total absence of it. Gravity on Phobos is somewhere between roughly 1,000th and 1/2000th of what you feel right now, wherever you are, whatever surface you are lying on. If you weigh 80 kilograms here on Earth, you would weigh something like 40 to 80 grams on Phobos, the weight of a small handful of paper clips. You would feel nothing pressing you down, nothing holding you in place. Walking would be out of the question in any ordinary sense. You would push gently off the ground and drift. Not float, exactly. There is still some gravity, faint as a whisper, pulling you back. But any movement would become enormous in its consequence. A normal walking stride would send you several meters into the air and carry you slowly, slowly back down over the course of many seconds. You would have to move in very small, careful increments, more like swimming through a place that has no water than like walking through a place that has no air. And if you pushed off too hard, if you misjudged it, if you jumped with the enthusiasm of someone who forgot where they were, you might not come back down. The escape velocity of Phobos, the speed you would need to reach to leave the moon entirely and drift off into space, is only about 11 meters per second. 11 meters per second is roughly the speed of a fast bicycle downhill. A strong throw by the standards of what a human arm can do can approach that. A genuine leap, if you were suited and equipped and momentarily careless, could send you drifting off Phobos into the void of the Martian system. You would not fall exactly, you would drift away. It is a thought that is both dreamlike and sobering, the way the best astronomical facts tend to be. Both Phobos and Deimos are tidally locked, the same way our own moon is locked toward Earth. Just as our moon always shows us the same face, the seas and craters we know, the pattern that has faced us since before human beings existed, Phobos always shows the same face to Mars, and Deimos does too. They are tidally captured, held in place by the same gentle mathematical force that links rotation to orbit when a small body circles close enough to a large one for long enough. So if you stood on the Mars-facing side of Phobos, Mars would never set. It would hang there, permanent and enormous, in that black sky above you. At the distance of 6,000 kilometers, Mars would appear more than 5 times the apparent diameter of our full moon as we see it from Earth, far larger. A vast disk, showing its plains and ancient craters, its polar caps and the vast dark splotches of its ancient volcanic provinces, all visible with your naked eye from your small dark perch 6,000 kilometers above its surface. It would not light the night the way the moon lights ours. Mars is smaller and darker than our moon, and the light it reflects is less. But it would be there, always, immense and rust-colored, hanging in the black, filling a great portion of the sky with its presence. Unmissable. Inescapable. The world that this small moon has always orbited, the world that is slowly, gravitationally pulling this moon toward it. There is no atmosphere on Phobos, not even a trace of one worth measuring. So the sky is not blue and there is no twilight and no soft diffusion of light. The stars are there in full force at all hours, as clear and many as they ever are in the depths of space, undimmed. Mars is there. The sun is there, smaller and less bright than it appears from Earth because Mars is roughly 1.5 times as far from the sun as we are, but still fierce and brilliant and tiny, a bright point rather than a comfortable disk. And all of these things are visible at once because nothing scatters or softens the light. The sky is an unmediated view of space itself, wearing no atmosphere between you and it. Temperatures vary considerably depending on where you stand and what time it is in the orbit of Phobos around Mars. On the sunlit surface, temperatures hover around -4 degrees Celsius, just a few degrees below freezing, cold, but not brutally so by the standards of outer space. On the night side, where the sun has not reached, and where Mars's reflected glow is not enough to warm the ground, temperatures drop far lower, plunging to extremes that no exposed skin would survive. The surface heats and cools rapidly because there is nothing, no air, no blanket of atmosphere, to hold the temperature steady. Beneath your feet, wherever you stand on Phobos, the ground is soft in the way that ancient dusty places are soft. The regolith, the layer of crushed and powdered rock built up over billions of years of tiny impacts, micrometeorites striking the surface endlessly over an enormous span of time, may in places be many meters deep. It is loose and fine, a kind of cosmic dust that has never been compacted by rain or life or the tread of anything with weight. A lander setting down on this surface would need to be careful. It might sink slightly. It might need wide, flat feet to spread its weight across the powder. The engineers working on MMX have thought about this carefully, running models and estimates to understand how soft and how deep the regolith might be in the places where the spacecraft would touch down. There is something both strange and gently melancholy about standing on Phobos in imagination and feeling that soft, ancient ground under your feet. Every grain of that regolith has been there for a very long time. Some of it is material that has never been disturbed since the early solar system. Some of it is ejecta from the Stickney impact, redistributed across the surface when the Great Collision happened. Some of it has drifted back from the faint dust tori that surround the orbits of both moons, settled back onto the surface it originally came from after a brief journey through space. And speaking of Stickney, from the Martian surface, an observer standing near the equator on a clear Martian night, watching Phobos rush across the sky, could see it, not just as a point of light or a pale disk, but as something with detail. Because Phobos's angular diameter in the Martian sky is large enough that the dark mark of Stickney, that enormous crater nearly half as wide as the whole moon, would be visible to the naked eye as a shadow or a blotch on the disk. You would not need a telescope on Mars to see the scar that almost destroyed its smaller moon. You would only need to look up. There is one more strange geographic fact about Phobos's orbit that deserves to be said slowly and clearly, because it is the kind of thing that sounds like a mistake the first time you hear it. Phobos orbits so close to Mars, and Mars is a planet with enough mass that its curvature matters, that from the polar regions of Mars, Phobos cannot be seen at all. It never rises above the horizon. If you were standing near the north or south pole of Mars, Phobos would be permanently hidden behind the curve of the planet beneath you. Its orbit is too low, too tight, too equatorial for the poles to catch a glimpse of it. Only observers within a certain band of latitude, not too far north or south of the equator, have access to the sight of Phobos in the sky. It is a moon that cannot be seen by everyone on its own planet, a companion that hides, and the phases, because Phobos moves so quickly, completing its orbit in just 7 hours and 39 minutes. The phases cycle at a speed that is almost dizzying to contemplate. From new Phobos to full Phobos and back to new again happens in the time it takes to have a long night's sleep. The crescent thickens and broadens and rounds and then shrinks again in hours. An observer watching from the Martian surface would see the lit fraction of Phobos's face change visibly over the course of a single hour, the way we might watch a time-lapse of our moon over the course of many days. It is a sky in a hurry on that side of things. Everything about Phobos's relationship with Mars is fast and close and urgent, unlike anything in the stately, slow-moving experience of moon-watching from Earth. Both moons also trail something behind them and ahead of them as they orbit: dust. Each time a micrometeorite strikes the surface of Phobos or Deimos, the impact kicks up a cloud of fine material. On Earth, or on the Moon, most of that kicked-up dust would fall quickly back to the surface. But on Phobos and Deimos, with their almost negligible gravity, a large fraction of the dust escapes entirely. It drifts off into the orbital path of the Moon, spreading out ahead and behind, forming a faint and tenuous cloud, not a ring in the vivid, bright sense that Saturn's rings are rings, but a torus, a donut-shaped haze of dust following each moon's orbit around Mars. These dust tori are too thin and too faint to see with the naked eye or even with ordinary cameras. They have been detected through careful instrumentation and modeling rather than direct observation, but they are there, these ghost trails of ancient rock, following the two moons in their orbits like the faintest possible echo of every collision that has ever struck these small, dark bodies over billions of years. It is a beautiful image if you let it form slowly. The two moons orbiting through their own halos of shed dust, invisible to the eye but real and measured, the accumulated wreckage of eons of micrometeorite rain, drifting quietly along the same paths the moons travel, as if the moons were very slowly, very gently, leaving traces of themselves behind. Now let's rest in some numbers for a while. Not complicated numbers, soothing ones, the kind that help you feel the scale of where these moons exist. If Earth were the size of a basketball, a large, familiar, holdable sphere, then Mars would be about the size of a softball, and Phobos in this comparison would be a grain of coarse sand, a single grain, not even noticeable if you dropped it on a table, and yet that grain has its own surface, its own craters, its own grooves, its own mystery of origin, its own doom, measured out in centimeters per year across the coming millions of years. The entire surface area of Phobos, every square meter of its lumpy, pockmarked, ancient exterior, is roughly comparable to the surface area of a large metropolitan area, not a continent, not a country, a metropolitan area, a city and its surroundings. In principle, every part of Phobos could be mapped the way we map cities, in detail with names and features and surveyed distances. We have not done all of that yet, but we have done much of it. Viking gave us the first maps. Mars Express refined them. MRO and HiRISE have given us color and detail. The Moon is small enough that it can be fully known eventually in a way that planets never can be. The Sun's light, traveling at the speed of light, takes a little more than 12 minutes to reach Mars and its moons from the Sun. So when you look at Phobos, when any camera captures it, you are seeing it as it was 12 minutes ago. Not a meaningful lag in ordinary life, but a real one. Phobos and Deimos exist always slightly in our past, even as we study them. And radio signals from Earth, which also travel at the speed of light, take between roughly 5 and 20 minutes to reach a spacecraft at Mars, depending on where the two planets happen to be in their respective orbits around the Sun. When Mars is on the near side, 5 minutes. When it is on the far side, 20. This is why no mission to Phobos or Mars can be guided from Earth in real time. By the time the command arrives and by the time any response comes back, 10 to 40 minutes have passed. Every spacecraft operating near Phobos must be intelligent enough to handle its own moments of crisis, because there is no one who could reach it fast enough to help. Idefix, rolling across Phobos on its small wheels in that faint gravity, will be making its own decisions in those critical moments, guided by the instructions given to it before any gap in communication, navigating the ancient dust by whatever autonomous judgment its engineers have built into it. Phobos completes more than 1,000 orbits of Mars in a single Earth year. More than 3 each day on average, though of course on Phobos there are no days as we understand them, just the endless cycle of orbit. The same face turned toward Mars. Mars hanging in the black sky, the surface moving through its extremes of temperature as the sun traces across it, and then falls behind the horizon, and then returns again. More than 1,000 laps around Mars in a year, patient and not patient, methodical and falling. The surface material of Phobos, when studied by spectrometers from orbiting spacecraft, shows characteristics that match some of the most primitive, ancient meteorites we have found on Earth, rich in carbon-bearing material. Similar to a class called D-type or carbonaceous asteroids, the dark, old building blocks of the solar system, the kind of material that formed in the cold outer reaches before anything warm and complex had yet developed. This is part of what makes the origin question so interesting. If Phobos is a captured D-type asteroid, that spectral match makes sense. But if it is made of material blasted off Mars, then Mars's early crust was surprisingly rich in this kind of primitive, carbon-bearing material, which would be remarkable in its own right and potentially significant for the long question of whether Mars was ever a place where chemistry more interesting than bare rock was occurring. Some measurements have hinted at something else in the subsurface of Phobos. Water ice. Not confirmed, not certain. This is where we must be careful and honest about what is measured versus what is inferred. But certain thermal and spectral analyses have suggested that beneath the dusty regolith, Phobos may hold water ice mixed into its deeper layers. If that is true, and MMX's sample return and surface measurements will help address this, it would be another layer of significance. Water ice on a moon of Mars, so close and so accessible, would matter to anyone thinking about the long future of human exploration of the Martian system. Which brings us to another thought, quieter and more speculative, but grounded in real mission concept work. Some space planners, thinking about the long arc of human presence beyond Earth, have looked at Phobos not just as a scientific target, but as a potential platform, a staging base, a low-gravity waypoint above Mars where material could be stored and equipment assembled and crews rested before descending to the surface below. The idea has not advanced beyond concept studies, and there is no concrete plan, but the thought has been thought, and the physics are not unfavorable. Phobos is close. It is low. It takes relatively little energy to reach compared with descending to Mars itself. It has, perhaps, water ice that could be converted to fuel or drinking water. And it offers a front-row view of the planet it orbits, Mars filling the sky, while work proceeds in the near-zero gravity of the Moon's surface. It is one of those ideas that sits at the edge of the far future and glows gently, not urgent, not immediate, but not impossible either. And then there is the color. Phobos is not a uniform shade of dark grey when you look at it in colour. Images from HiRISE, the high-resolution camera aboard Mars Reconnaissance Orbiter. There are regions that appear slightly bluer and regions that appear somewhat redder. The material inside and around Stickney crater, the Great Impact Scar, appears bluer than the surrounding terrain. The working interpretation is that this bluer material is fresher, less weathered by the slow process of space weathering, the constant bombardment by solar wind particles and micrometeorites that gradually reddened ancient surfaces over time. Stickney exposed deep material that had not been on the surface long, and so it carries a different color signature. Younger in a relative sense, less processed. The impact that nearly shattered Phobos also, in a sense, revealed something interior and fresh for the first time in a very long time. There is something in that image, the wound that almost ended the moon, revealing what was inside, the scar as a window. And now we come to the end of the list, the last few facts. The ones saved for last because they are not really individual facts at all, but the shape of everything we have been talking about distilled. Phobos is doomed. That is not a dramatic word used loosely. It is the accurate word, and it deserves to be said quietly and without exaggeration, the way that certain true things deserve to be said. Every year, Phobos falls a little closer to Mars, about 1.5 to 2 centimeters per year. The width of a few fingers, the distance you could cover by sliding your hand across a table, that is the annual portion of Phobos's long, slow fall. Each orbit is fractionally lower than the one before. Each pass is fractionally faster. The tidal forces that govern this, the same forces that govern the drift of our own moon away from Earth, have been acting on Phobos since long before any life existed on any world we know of, and they will continue acting on it long after. In roughly 30 to 50 million years, the estimates have a range because the interior structure of Phobos is not fully known, and the interior structure matters for how tidal forces propagate through the body. Phobos will approach the Roche limit. The Roche limit is the distance from a planet at which tidal forces, the difference in gravitational pull on the near side of a body versus the far side, become strong enough to overcome the internal cohesion of the body itself. Inside the Roche limit, rubble piles and loosely bound bodies are torn apart by the tidal stretching. Solid rocks can survive a little longer, but even they are eventually overwhelmed. Phobos, with its low density and its likely porous rubble pile interior, will probably not survive this encounter intact. When it reaches that critical distance, it is expected to break apart, not in an explosion, not suddenly, from a human perspective. But the tidal forces will exceed what holds the moon together, and the pieces will spread. First into a diffuse cloud of debris along the orbital path. Then, over time, that debris will spread and flatten and settle into a ring around Mars. A faint ring, not the spectacular icy rings of Saturn, but a real ring nonetheless. Mars, for the first time in its observable history, would have a ring of its own. That ring would not be permanent. Over additional millions of years, the particles of which it was made would gradually rain down onto Mars, drawn inward by the same forces that brought Phobos itself to destruction. The ring would thin and fade and ultimately disappear, leaving Mars once again unadorned. The whole cycle, the infall, the breakup, the ring, the rain of debris, would take tens of millions of years to complete. We will not see any of it. No human alive today, and no human who will live for as long as our species has existed, will witness even the beginning of this process. 30 million years is more than 1,000 times the span of recorded human civilization. It is a future so distant that the continents of Earth will have shifted considerably from where they sit tonight. But the process is underway right now, in its slow and unhurried way, measured in those 2 centimeters per year, accumulating. There is something oddly comforting in this if you let yourself feel it. The universe operates on time scales that dwarf us completely. The story of Phobos's doom is a story that will unfold long after we are gone, long after anything we know is gone, in a solar system that will still be quietly going about its business without us. Phobos will be falling in its slow way tonight and next year and in a century and in 10,000 years, entirely regardless of whether anyone is watching or knows or cares. And Deimos. Quiet Deimos. The smaller, smoother, more distant moon, orbiting out there at 23,000 kilometers, crossing the Martian sky so slowly that a Martian observer would see it rise in the east and not set in the west for more than 2 full Martian days. Deimos is doing the opposite of Phobos. Deimos orbits just outside the synchronous altitude, the distance at which an orbit takes exactly as long as the planet's rotation. Outside that altitude, tidal forces work in the opposite direction. They nudge the orbiting body outward, not inward. They give it a fraction of energy rather than taking one away. This is what our own moon experiences. It is moving away from Earth at about 3.5 centimeters per year, pushed gently outward by tidal forces, and Deimos is doing something analogous around Mars. The rate is slow and the destination is uncertain. Some models suggest Deimos will eventually drift far enough from Mars that Mars's gravitational grip will weaken to the point where encounters with other bodies, or the perturbations of Jupiter's gravity at some distant future point, could gradually redirect its path. Perhaps it will enter a wider and wider orbit. Perhaps, far in the future, at a timescale even larger than Phobos's doom, Deimos could drift loose entirely and become an independent body in the inner solar system, a small and dark asteroid wandering among the planets, the way it perhaps once wandered before Mars captured it, if that is indeed what happened. We do not know. The models have uncertainties. The future of Deimos on very long timescales is genuinely unclear. But the direction is clear. Deimos is moving away. So here they are, the 2 small moons of Mars, named Fear and Dread, the sons of the war god, the companions of Ares in the ancient myths, the words Henry Madan found in Homer's Iliad, and suggested to Asaph Hall, who discovered them both in August of 1877 from a refractor on a hillside in Washington, while his wife urged him not to give up. One of them is falling, losing 2 centimeters of altitude a year, scarred half through by the blow that made Stickney grooved and porous and dark, rising in the wrong direction twice a night over the red equatorial plains below, falling, and in 30 or 50 million years destined to be shattered into a ring by the very planet it circles so faithfully, so fast, so close. And one of them is leaving, smooth and quiet and slow, drifting outward year by year, barely noticed, showing the same face always toward the planet it is, in the longest sense, departing. Small enough that a thrown stone could escape its gravity. Covered in dust so fine it smooths over the craters that pockmark it. Rising in the east, setting in the west, taking nearly 3 full days to cross the Martian sky, unhurried, moving in the direction of eventually somewhere else, Fear and Dread. Both fated in the end to leave Mars alone. There is a kind of poetry in that which does not require you to believe in poetry or in fate or in anything beyond the mechanics of orbital dynamics and tidal evolution. The poetry is in the facts themselves. The war god's moons, named for the things that go with war, are departing. One in catastrophe, one in slow and quiet withdrawal. And Mars, the red planet, will be left in the end without either of them. Without the one that rose backward in the west twice a night. Without the one that crossed the sky over nearly 3 days and glowed like Venus. Both gone. In the end. We set out at the beginning of this long, quiet journey, wondering about 2 small moons. You may have settled in a little deeper by now. The lamp may be lower, the sounds outside may have softened. And we have found over the course of these 100 facts that 2 small moons are not a small thing at all. They carry a discovery. 1 astronomer, 1 refractor, 8 days in August 1877, a wife who said, "Keep going." They carry names out of Homer, out of a mythology that saw fear and dread as literal companions of the god of war, as real and present on the battlefield as the spear and the shield. They carry a literary mystery that is more charming than it is meaningful. A novelist in 1726 who imagined, with a guess educated by the spacing of known moons, that Mars had 2 small ones, and the guess happened to be close enough to be remembered. They carry craters within craters, a scar that nearly ended one of them, grooves that may be the first visible sign of a breakup still 50 million years in the future. They carry the dust of their own surfaces in faint invisible halos along their orbits. They carry the possibility, perhaps, of water ice and of carbon-rich material that predates the planets themselves. They carry in their composition perhaps a piece of the early history of Mars that we can reach in a way we cannot reach Mars's ancient buried surface, because a spacecraft can land on Phobos and come home, and Idefix can roll across its ancient ground, and 10 grams of material can be brought back to a laboratory on Earth and opened and read, and they carry their opposite fates. Phobos falling, always falling, the inevitability of it measured in finger widths every year. Deimos leaving quietly, in no particular hurry, in the direction of somewhere we cannot fully predict. You are lying somewhere right now at whatever time it is in your corner of the world. And overhead, not overhead exactly, but out there, in the direction of a point in the sky that shifts as Earth rotates and orbits, Mars is somewhere, and around it, Phobos is completing one of its 3+ daily orbits, and Deimos is making its slow 2.5-day crossing, and the dust trails drift in the vacuum, and the Stickney crater sits silent and enormous on the smaller moon's pocked face. And no one is there to see any of it, no one is there yet. But something is coming. The universe is very old and very patient. These 2 small moons have been doing what they do for hundreds of millions of years at least, possibly far longer, and they will go on doing it long after every question we have asked about them tonight has been answered and forgotten and asked again by someone else. The infall of Phobos is the infall of Phobos. The drift of Deimos is the drift of Deimos. They do not know we named them. They do not know we found them on those 2 August nights in 1877, or that we mapped their craters, or that we are sending a machine to gather 10 grams of the surface and bring it home. But knowing this, the knowing of it, belongs to us. This strange small human capacity to sit in the dark or lie in the dark and reach outward with instruments and mathematics and imagination and come back with the shape of things 40 million miles away in exact and vivid detail. The 7 hours and 39 minutes, the 1.8 centimeters per year. The 9-kilometer crater that nearly broke a moon only 27 kilometers across. These are not approximations or vague impressions. These are the actual numbers, and they belong to anyone who has spent a little time in the dark being willing to listen. That is what you have done tonight. And it is a good thing to carry into sleep the specific, quiet fact that 2 small moons are out there orbiting Mars right now, as they have always done, as they will do for as long as we can foresee, and that you know their names and their sizes and their fates, and the names of the people who found them. Asaph Hall, who almost gave up. Angeline Stickney, who said, "Keep going." And the crater that bears her name, half as wide as the moon it marks, the wound that revealed what was inside. If you enjoyed this slow journey through the Martian sky, A like and a subscribe would mean more than you might think. Small creators like me rely on your support to keep making these. And if you have a moment before you drift off, I'd love to know, where are you listening from tonight? And what time is it in your corner of the world? Until next time, good night from up here in orbit. I'll keep watch while you drift.